Hello students, welcome back. Previously we studied implicit relation. We studied thoroughly, got to the bottom of it, plus some optional topics. So we don't have to get back there. Let's go to the next topic, implicit differentiation. Let's begin with this relation. And here's a graphical expression of the relation, by the way. Okay, all right. From here, let's take the derivative. How do you take the derivative? Well, let's take a naive approach. The derivative of x to the third power, 3x squared. Does it look good? Okay, next, the derivative of y to the fifth power. How about that? All right, power rule. And the derivative of constant 3. That's 0, no problem there. And then we have a problem, derivative of this. Okay, x squared times y to the third power. We're going to consider this derivative a bit later. So let's postpone that. Prime means you're going to take the derivative. All right, does it look good? Actually, not yet. Something is still missing. What's missing here? Let's copy and paste it here. Okay, all right. This one here, which I just highlighted in blue, x to the third power, becoming 3x squared. No problem there. Because we are taking the derivative with respect to our variable x. Both x and y are changing, but you are taking the derivative with respect to a certain variable here, and that should be your x. After all, the problem said, take the derivative by x. But then again, look at this. Y to the fifth power becoming 5y to the fourth power. We have a problem here. Y is not our main variable, but we did calculation as if that's the case. Can we actually do that? The answer is no, we can't. Because at least locally, y depends upon x. So as a matter of fact, y to the fifth power is, as a matter of fact, a function y of x to the fifth power. So the chain rule applies. Outer function is fifth power function, so power comes out as coefficient. And then nothing changes inside, so y of x stays there. And times derivative of the inside. Let's use the other color here. Let's use green here. So green here. And I want to emphasize this one with red. Red is a little bit more conspicuous, so I'm using red for something that should be the most conspicuous. And y prime is the important term here in this implicit differentiation technique. What happened here? This is actually a chain rule. Fifth power function is the outer function. Inside I have y of x. Apply the derivative, 5 comes out and subtract 1 from the power. That's the derivative of the outer function. And inside never changes, so it's simply this one stays as y. And then we multiply the derivative of the inside, y prime of x. You see, this y prime of x highlighted in red came from the chain rule. If you use that viewpoint, y is actual y of x to the certain power, then x squared times y cubed can be rewritten this way as well. And then we can use the quotient rule, the product rule. Not the quotient, product rule, The derivative of the first function times the second function plus first function times the derivative of the second function, 3y to the second power. Let's put this dot in there as well. And then by chain rule, we have to multiply the derivative of the inside. Let me highlight this in green. Red, y prime is highlighted in red. So this x squared becoming 2x That's a derivative computation, and the main variable is x, so everything is okay. This one is just copying, so no problem here. Now, the other part, x squared is copying, no problem. Taking the derivative of y of x to the third power, it's basically the same as before. It's a chain rule. Outer function is third power, so 3 comes out. Subtract 1 from the power, again the chain rule. Inside stays the same, again the chain rule. And then finally, the derivative of the inside, y prime. Again, the chain rule. The key is chain rule, chain rule, chain rule. As a matter of fact, this is a bit too cumbersome, right? So most people calculate like this. So x cubed becoming 3x squared. No problem there. Y to the 5th power, 5y to the 4th power, derivative computation. And then by chain rule, we have y prime. So whenever we have the derivative formula for y, y prime pops out. The reason is the chain rule. All right? And then we have 0, no problem there. 3 is a constant, so that becomes 0. Now let's apply product rule here. The derivative of the first function, x squared, so 2x, times the second function, x to the third power. All right? First function, x squared, times the derivative of second function, now y to the third power. Apply the derivative rule by y, 3y squared, and then y prime pops up. The reason is the chain rule. But going back to chain rule like this and then redoing everything is too cumbersome. Far more effective and practical way is to remember this. Whenever you apply the derivative rule to y, y prime pops up. So y to the 5th power becomes 5y to the 4th power, automatically y prime pops up. Y to the 3rd power becomes 3y squared, automatically y prime pops up. Some people prefer the German notation, dy dx expression. Oh, by the way, this is a derivation using the chain rule. Yeah, y of x to the 5th power, y of x to the 3rd power, and then chain rule. Outer function, and then inside stay the same, and the derivative of the inside, something we repeated earlier. But just look at this. Too complicated, right? Really hard to follow. Stick to the practical method. By the way, many people rewrite this one into German notation instead of y prime, dy over dx like this. Instead of y prime, dy over dx like this. It's quite common to do it this way. Our textbook author almost exclusively does dy over dx. Did I say almost? I think he almost, without almost, he exclusively used dy over dx only, I think. And do you have to do it that way? Well, me personally do not really think so. So in my opinion, y prime is okay. But there are some people who gives no credit for the student who are using y prime. The underlying reason is when you take the derivative, when you have more than one characters, you have to specify with respect to which character you're taking the derivative with. And this way, dy over dx is explicitly there. We are taking the derivative, all this computation is with respect to x. If we do it this way, it's a bit less certain, according to their logic. But then again, nowadays, if your expression does not match with computer algebra system, then it's nearly useless. This expression here does not work with computer algebra system. This one does. So I prefer this top expression much better. Partly because I'm closer to applied mathematician than pure mathematician. So I'm very much into computer programming. Okay, not as much as into computer scientists, but in terms of mathematical realm, I'm into symbolic computation. So I like this expression, y prime expression, better. And of course, if you see y prime, it's clear that y is not the variable, it's something else. It should be x, right? Why do I have to specify x this way using the confusing and intimidating dy dx expression? I disagree with the people who take points off for using y prime expression. But if you prefer to use dy dx expression, just like our textbook author, and overwhelming majority of the textbook writers, go ahead. I'll go with overwhelming majority of computer algebra system programmers. So textbook approach, computer approach are kind of conflicting each other. And my experience is students usually do better with simpler prime expression. That's another motivation for me. So we took the derivative implicitly like this. That's the key. And then let's solve for y prime to find out the derivative y prime expressed in terms of x and y. How do I do that? Let's solve symbolically. It's a bit intimidating because there's so many characters, but the idea is actually simple. You see, this is a linear equation, y prime to the first power only. So you can use the technique for solving a linear equation. Consider this as just a number. That 2 is just a number. That 2 is just a number. That 2 is just a number. So get all the y prime terms on one side, all the numbers to the other side. 5y to the fourth power y prime minus x squared. Let's just 3x squared y squared. So all the y prime terms on the left hand side. Everything else to the other side. So negative 3x squared plus 2x y to the third power. Let's write it like this. I don't like to have too many negatives flying around. Okay, alright. All the y prime on one side, everything else to the other side. Now factor y prime out. Okay, let's go to the final step. We had 2 y primes. Here we have 2 y primes flying around. Here 2 y primes still, but they're all on the left hand side. Now after factoring out, only 1 y prime left. Divide this away, then I'm going to get the answer. Y prime is equal to this expression here. Divided by the coefficient. Sorry about this typo here. Expanding the font. That's how you find out the derivative and complete your computation. Taking a derivative, after some exercises, you'll feel comfortable. Solving for y prime, I don't think you'll ever get used to it. But both are related and both are required. You need some practice. Let's have more practice in a separate video.